This is section 15.4. I'm going to be discussing heat capacities. The molar heat capacity is the amount of heat that's required to change the temperature of 1 mole of a material by 1 Kelvin. The molar heat capacity at constant volume is the same for every ideal monatomic gas. So you can see there the heat capacity at constant volume, which is why you have a little subscript V, is going to be equal to 3/2 times R. That's about as constant as it gets. So for an ideal diatomic gas, including rotational but not vibrational kinetic energy, then you see an increase. You see an increase to 5/2 R. Translational motion is going to be motion in your three different dimensions. Rotational motion is going to be rotating about specific axes. So that's going to add some degrees of freedom here regarding heat capacity. And then you can see vibrational motion as we're talking about that, as to how these molecules sort of as if they were connected here with a spring, how they kind of bounce back and forth with each other. So back in section 14.4, we defined specific heat in terms of the measured amount of heat needed to change the temperature of a specified quantity of material by a particular amount. We didn't attempt to predict specific heat on the basis of more fundamental considerations. In some simple cases, these numbers can be predicted. When we're dealing with the heat capacity of gases, it's often convenient to describe the quantity of a substance in terms of the number of moles rather than the total mass. And that's why we go into the molar heat capacity. So the amount of heat needed for a certain temperature change is proportional to the temperature change and to the number of moles of the substance. And then C is going to be the constant, the heat capacity, in this case, the molar heat capacity, because we're talking about moles, for the material. It's the way you make sure that the equation is calibrated, so it becomes an equation. So comparing this to this and recalling the relationship here, we can see that the molar heat capacity of a material is related to the specific heat by this relationship. So this is the relationship of specific heat and molar heat capacity. M obviously is going to be the molar mass of the material. So the heat per mole equals the heat per unit mass times the amount of mass per mole. So for example, the molar heat capacity of liquid water is going to be this multiplied by the mass, and then you get your molar heat capacity. So in these discussions, we're going to keep the volume of the material constant, so there's no energy transfer through mechanical work. Because if you let the gas expand, it's going to do work on the moving walls of the container, and that's going to complicate matters. So here we're just going to hold it constant. All right. So in this section, you're going to see a brief introduction to the analysis of heat capacity of gases on the basis of simple kinetic molecular models we've discussed in the last section. So in that model, the molecular energy consists only of kinetic energy associated with a translational motion of point-like molecules. It turned out to be this. When the temperature changes by a small amount, the corresponding change in energy is going to be this. So the change here is going to be the change here. That's the difference. From this definition of the molar heat capacity at constant volume, you're going to have this relationship as well. So if the translational kinetic energy represents a total molecular energy, as we have assumed, then the heat and the change in the translational kinetic energy must be equal. So you set this equal to this, and that's where that equation comes from. And that is the molar heat capacity of every gas whose molecules can be represented as points. So for comparison, this particular table gives measured values of C sub V for several gases. We see that for monatomic gases, the prediction is pretty much right on the money. Again, this is for monatomic. Diatomic and polyatomic, where you can see the relationships here, where you've got several different types of elements, or even just molecules of the same element, but they're tied together. You can see the differences there. So if you start looking for diatomic and polyatomic, then you've got to make things a bit more robust in the model. So if you take a look at a diatomic molecule, you've got 2 point masses. These things can rotate. If we want to make things even more complicated, we can add in vibrational motion. When you do these things, it turns out that the additional energy of rotation and vibrational motions is also proportional to T. So if you take a look at the rotational, average rotational kinetic energy of kT per molecule or Ag per mole, then it turns out this is the relationship. And that changes your molar heat capacity here to 5/2 R. Also, if you add in vibrational motion, you start ending up having to deal with quantum effects, and we're not going to worry about that in this particular discussion.